In this video, I'll be covering every single test of convergence and divergence that you have learned in Calculus 2. So this is the perfect video to watch if you're reviewing for a final or you have a specific test on divergence or convergence for series. The first one we're going to cover is the divergence test. This one is the most simple one, but there's a condition that you must keep in mind. The divergence test can never determine convergence. It can only tell you if a series diverges. It cannot tell you if a series converges. Other than that, it will be inconclusive, right? So the two results for this are either diverges or inconclusive for the divergence test. So let's go ahead and cover the divergence test. So as the limit as n approaches an infinity for a of n, if this sequence does not equal 0, right, then your series diverges. So let's give you an example. Let's say that we have a series. Let's say that we have a series n squared, right? Let's say we have a series n squared. Let's just put that in red for consistency. Does this series converge or diverge? Well, you don't have to use limit comparison or any other complicated test. You can just use divergence test for this. All right? So let's go ahead and take the limit as n approaches infinity for n squared. So if you directly plug in infinity into n, you get infinity squared, which is plain old infinity, right? Infinity squared is still equal to infinity. So since this does not equal 0, your series diverges. All right. And let's go ahead and test an example for the case where it's inconclusive. 1 over n in this case. So maybe some of you guys already know 1 over n harmonic series, it automatically diverges. But in the case of the divergence test, you actually get inconclusive. And I'll show you why. So as the limit as n approaches infinity, so you'll basically get 1 over infinity here. But 1 over infinity is, sort of approaching 0. So we should say it's equal to 0. Since you're doing that divergence test here, right? You're taking n to approach infinity. But you get some value that's actually equal to 0, right? You actually get an answer that's equal to 0. You get a result of inconclusive, right? This right here is inconclusive. And remember, the divergence test cannot tell you convergence. It doesn't tell you if a series converges, x, 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 x. It only tells you if a series diverges. Well, in the name, it says divergence test, so of course you can keep that in mind. But remember, the condition for divergence is simply if n approaches infinity and your sequence does not equal 0 as n approaches infinity, right? That just plain old diverges. But if your limit does equal 0, right, then you get an inconclusive result. You have to use another test. In contrast to the divergence test, the p-series test can tell you if a series converges or diverges. It can tell you both, okay? So this is the format of how or when you can use the p-series test. If you have some constant, usually specified by 1, right, over n to the power of something. So an example of this would be 1 over n to the power of 3, right? Or 1 over n to the power of 1, or 1 over n to the power of 4, or 2. These can all be examples of the case of a series where you can use the p-series test to determine convergence or divergence. Let's go ahead and tell you the conditions, and let's go ahead and work on a couple quick problems. So the conditions for the p-series test is if p, and I'll specify what p is later, but if p is less than or equal to 1, then your series, maybe I should put this down here in the divergence part, then your series diverges. Right. And if p is greater than 1, then your series must converge. And what is p? P is simply whatever the series n is to the power of. So in this case, you have a sum 1 over n to the power of 2. In this case, p is equal to 2, right? Since n is to the power of 2. So since p is equal to 2, can we determine convergence or divergence for this test? Well, look at the conditions for the p-series test. If p is greater than 1, then your series converges. Therefore, this guy converges since p is equal to 2 and 2 is greater than 1. All right. How about in the case of this, 1 over n? Well, 1 over n is technically 1 over n to the power of 1, right? So if you have 1 over n to the power of 1, you can simply write down that p is equal to 1, correct? That is what n is to the power of. Well, since p is equal to 1, does the series converge or diverge? Well, the series diverges. Since the condition of divergence is if p is less than or equal to 1, that is the times when your series will diverge. So since p is equal to 1, and the condition states if p is less than or equal to 1, the series diverges, then this guy right here diverges. So hopefully you guys get the pattern of that already. If anything greater than 1, your series will diverge. Converge. And a better example of this would be probably at least a more complicated example of this would be if you had n root to the power of 3. Right. This right here can be rewritten as, if you know your power rules, but this right here can simply be rewritten as 1 over n to the power of 3 over 2. And since 3 over 2 is greater than 1, right, p is equal to 3 over 2 in this case, since 3 over 2 is greater than 1, then your series will converge in this case. And also, in the case of a square root, right, if 1 over square root of n, what is p here? Well, this can be rewritten as 1 over n to the power of 1/2, and p is less than 1 in this case, correct? 1/2 is less than 1. So in this case, the series diverges. Now, you might be wondering how in the world does that work? I don't know. Like if you try to find the integral of 1 over n, you're going to realize that, yeah, the integral goes on to infinity. That could be a hint as well. But apparently anything like 1 over n doesn't grow quick enough to reach, to converge, right? Or decrease fast enough to converge. So I guess that's why 1 over n is called the harmonic series and diverges. The geometric series test is among one of the easier tests because all it does is require you to do some arithmetic and a little bit of comparison, of course. But this right here is, in essence, the geometric series test. So if you don't understand what these numbers mean, of course an example will always help. But let's first talk about the conditions. R is going to be some ratio, right? Remember that R is some ratio. R stands for ratio, right? But here's an important condition that must be met. R must be less than 1 in order to do what I'm doing here. More specifically, R just needs to be the absolute value of R just simply needs to be less than 1. If this is the case, then you can use this formula to determine where the geometric series actually converges at. You can know the number, right? Instead of just converging or diverging, some very general terminology, you'll know the actual number that the series will converge at. So this right here, if R, the ratio, is less than 1, or the absolute value of R is less than 1, then you can use this guy to determine where your series will actually converge at, the number your series will converge at. Now, if the absolute value of R is greater than or equal to 1, then your series diverges. And you can just write down diverges. You don't have to use anything else, right? Diverges is an answer. So what I think will help a lot of you guys see this better is if you do a practice problem, right? You're probably wondering what is A, what is R, what is even N at this point, right? So A, let's say A is equal to 3, right? You have a 3 and you have 1/2 here to the power of N. This right here is your series. It's an example problem. Now, keep in mind, the problems I'm going to give in this video aren't going to be as in-depth. If you want more specific questions, then go ahead. I'd link all the divergence and convergence test videos down in the description. But those will have problems that you'll likely find in your exam, right? Not as obvious problems to solve. This one has the exact format of the geometric series test, but sometimes you might actually see the exact format. So if you're curious, go ahead, watch those. But let's go ahead and solve this. So if we follow this format of the geometric series test, we'll know that A is outside of your brain, is outside of your parentheses of r, right? So r is usually going to be in parentheses to the power of n, or the power of something, okay? So in this case, we actually know that r is equal to 1/2, right? The ratio between each next part of the sequence is 1/2 of the next one, and the starting value of the sequence is a, right? And in this case, a is equal to 3. Sorry, I should have put this, if I want to be more mathematically accurate, or even right in this case, I should have said that these start off at 0. So let's go ahead and look at this problem. We have a equal to 3, and we have r equal to 1/2. That's all we need. We could simply use this formula, a over 1 minus r. And you can actually determine what number your series converges at. So 3 is on the numerator. 3 over 1 minus r, which is 1/2. So we have 3 over 1/2 in this case, and 3 over 1/2 is simply equal to 6. So this series actually converges at 6. Let's go ahead and do another problem. Let's erase this. Take a look at another very simple problem. Let's say the starting value is 5. Let's say the ratio is 3 over 2 to the power of n. Well, in this case, we already know that the series diverges, right? Since r is greater than, or at least the absolute value of r is greater than 1, since r is equal to 3 over 2, we know that this series diverges. So that's really all the geometric series test is. If r is less than 1, or the absolute value of r is less than 1, then you can use this guy to determine, or this formula to determine whether or not, or where, sorry, not whether or not, where your series actually converges at, or what number your series actually converges at. And if r is just greater than or equal to 1, your series diverges. That's all you need to know. Well, we are at the comparison tests now, but here's the thing about the comparison tests. This direct comparison test has an extremely annoying condition. Okay, the conditions for this test need to be very carefully interpreted. So, of course, I'll specify as much as I can how to interpret them. But first thing you want to know about a comparison test is, well, you're comparing something, right? So this is what we call, by basic convention, a of n. All right, it's just a of n just represents the series, or the first original series. But how about our second series? What are we comparing this guy to? Well, we're comparing it to something called b of n. All right, so b of n is the compared series. A of n typically is the original series. So what is b of n? Well, b of n is simply just the series where you ignore the constants, ignore the numbers that have the smallest power, right? Basically, I just cancel out everything but the largest powers in the numerator and the denominator. So in this case, plus 3 has n to, technically it's times n to the power of 0, right? N to the power of 0 is 1. Technically, this is with the lowest power, 0, right? So we just completely ignore it. Boom, get that out of here in our compared series for b of n. And since there's really no powers in the numerator, you could just leave it the same. Okay. Usually if you had a constant like 10 as well, you would just simplify it to 1 in the compared series. And if you had a single constant in the numerator, you just simplify it to 1 usually for these comparison tests. So now that we have a of n and b of n, what do we do with this? Well, we need to meet this specific condition for the comparison test. And that specific condition is, first off, your series need to be greater than 0. And b of n must be greater than a of n. All right, so what do I mean by this? Well, if we take a look at our series, a of n, 1 over n squared plus 3, greater than or equal to technically, and 1 over n squared is b of n greater than a of n. Well, if you take a look in the denominator, let's go ahead and test out an example, n is equal to 1. Okay, when n is equal to 1, we have 1 over 1 squared plus 3, correct? So we have 1/4 here. And when n is equal to 1, we have 1 over 1 for b of n. So clearly 1 over 1 is equal to 1, and 1/4 is less than or equal to 1. Now, let me just put a less than or equal to 0 here, because I guess you could use the comparison test in those cases, but I mean, like, most of the time you're not going to get a series that's just equal to 0. Like, that makes absolutely no sense. Why would someone test you on that? So I guess I'll put this here for more generality. But some textbooks you might just see it greater than 0, and some of them you just might see them just have to equal. Some textbooks you might see this, some textbooks you might see this. Okay. So in this case, we need to know that b of n is greater than a of n, right, for all terms. So if we take a look at the logic of this series here, we realize that the n squareds will always equal the same value, correct? But since we're adding 3 onto the denominator for a of n, you're always going to get a larger denominator for a of n than for b of n. And since you're always going to get a larger denominator, that just means that the value of the number is smaller, right? So now that we've met this condition, we need to be a little more careful with more conditions. And that is, if b of n converges, then a of n also converges. That is if you meet this condition. And if a of n diverges, then b of n must also diverge. Here's the annoying thing about this. It only can follow this order. Okay? Keep this in mind. If b of n converges, so if this guy converges, then a of n converges. All right? And if a of n diverges, then b of n also diverges. But what if you figure out that a of n converges first? Well, if you figure out that a of n converges first, that's inconclusive. Okay? The only reason or the only way you can determine convergence is if b of n converges. You cannot say they converge if a of n converges. Okay? Now, keep in mind, if you figure out that a of n converges, then you already have your answer. You don't have to find b of n. So there's that. But how about if b of n diverges? Right. Nowhere in this does it state if b of n diverges, then a of n diverges as well. So if you figure out that this guy diverges, that doesn't necessarily mean a of n diverges as well. So yes, the conditions are very annoying. Okay, you can only follow these exact steps. If b of n converges, so if the compared series converges, then a of n also converges. Now, if you figure out that b of n diverges, that doesn't necessarily mean a of n diverges either. So keep that in mind, okay? That's why I said the conditions for this test are very annoying. But let's actually solve the rest of this problem. You're going to realize that we need to determine whether or not b of n converges to tell if a of n converges, right? Well, we can simply use a very simple tests for this. Most of the time, it's going to be p-series test. So p is equal to 2 here. And since p is greater than 1, this guy, this b of n, converges. And, you know, we use the direct comparison test. Since b of n converges and we meet this condition, since b of n converges, then this guy also converges. Plain and simple. So I'm going to give a little foreword on this. I mean, like, I'd recommend for most cases you just use limit comparison test. It's more applicable in all situations, and you really don't have to think about whether or not you have to use the direct comparison test or limit comparison test. So if you have trouble determining whether or not what test to use, just use limit comparison. Most of the time, you're just going to use limit comparison. If you can use direct comparison, you can use limit comparison. Okay, so just use limit comparison most of the time, and the conditions are significantly less annoying. And I'm going to go ahead and cover the limit comparison test exactly on the next test. Let's go ahead and talk about that. Well, I mentioned limit comparison test in the previous problem, but here's why it's significantly easier to just use limit comparison test for anything where you have to use the comparison test for. First things first, comparison test, you're comparing again, right? So you have to find some b of n series. So in this case, this guy right here is a of n, and we need to find b of n. So what is b of n? Well, b of n is another series where you just simply take out all of the exponents that aren't the largest exponents, or the largest powers in the numerator and denominator. So in this case, we have 3 times n over 2n to the 4th. here's the thing about the limit comparison test. When you find b of n, let's write down b of n here. When you find b of n, you usually just want to take out the constants, right? So you can just simply ignore the constants or the coefficients in front of all the numbers, and you can get something that looks like this. Well, the thing about this guy is that you can actually simplify it more, right? N over n to the power of 4 is also equal to 1 over n to the power of 3. So this right here is our compared series. Well, what can you do with this? Well, you need to take a limit. So, as the limit as n approaches infinity for a of n over b of n is equal to some value, you can call it c, you can call it L. I think most textbooks call it L, so we're going to call it L. And this L is the heart of the conditions for your limit comparison test. So let's go ahead and write out the conditions. If L is between 0 and infinity, then both your series converge and diverge together. So compared to the direct comparison test, if L is between 0 and infinity, then both the series converge and diverge together. So what does this mean? That means if b of n diverges, then a of n diverges. If b of n converges, then a of n converges. If a of n converges, then b of n converges. And if a of n diverges, then b of n also diverges. Basically, whatever you get, whether or not one of the series, a of n or b of n, doesn't matter, converges or diverges, the other one must do the same. And there's also more conditions that aren't going to be as common, right? These basically just, you might not actually see these on your test, but I'll write them down, of course, because I'm covering everything. But basically, when L is equal to 0, the only thing that you can determine out of this is if b of n oh my god, I got hiccups and a cough. If b of n converges, then I guess I'll put a comma. If b of n converges, then a of n must also converge. All right. And this is the only thing you can determine. If b of n diverges in this case, when L is equal to 0, you're going to have no idea. And if, let's use a different color for this, I guess. And if L is equal to infinity, then the only thing you can really determine is if b of n diverges, then a of n must also diverge. All right, so keep these conditions in mind. These are more specific than this one, the upper one, but most questions you're just going to get the top condition, really. So if, I actually have to solve the limit now. Where do I put these conditions? You know what, I'll erase them, and you can go back and forth, but I need to make space to solve the limit. I guess I could erase the title. Whatever. So the limit, remember, was a of n over b of n, okay? So let's go ahead and write down a of n. A of n is 3n plus 5 over 2n to the 4th minus 2n squared plus 1 over b of n, which is simply 1 over n to the power of 3. Now remember, for the condition of the limit comparison test, we need L to be between 0 and infinity for the very general condition, right? Basically, that condition states, remember, a of n converges, b of n converges, they converge together. And they diverge together as well. So let's solve this limit. And you might be wondering, how in the world do you solve this limit? Well, I'll show you. So it's n approaching infinity for this guy. You basically can just evaluate this. First off, remember, if you're dividing by some another fraction, multiply the reciprocal. So if you evaluate this, you get 3n to the 4th plus 5n to the 3rd over 2n to the 4th minus 2n squared plus 1. All right, and since we're taking a limit to infinity, we only care about the largest exponents in the numerator and the denominator. So what are the largest exponents? Largest exponents are 3n to the 4th over 2n to the 4th, right? Everything else, smallest powers, smallest exponents, whatever. Okay, so since these don't, this right here isn't n to the power of 4, this is n to the power of 3, which is less than n to the power of 4, we can ignore it. And so for the rest in the denominator. So if we erase all this, then we get left off with this guy right here. And this guy can simply be simplified. N to the power of fourth will be canceled out, so we get 3 over 2. And remember, this is equal to L. And when L is between 0 and infinity, then both the series converge and diverge together. So all we need to do is determine whether or not one of them converges or one of them diverges. So let's look at B of n. Usually that's the easier one to determine whether or not it converges or diverges. Which, if it isn't, then I'm not certain why you would be using the limit comparison test. If A of n is easier to determine whether or not converges or diverges. But let's go on. So in this case, this is just a p-series test, right? So this is 1 over n to the power of 3. And since p is greater than 1, we know that B of n converges. And since we actually meet this condition, right? Since we meet the condition that L is between 0 and infinity, that means both series, A of n and B of n, converge and diverge together. So since B of n converges, then A of n also converges. Now, if you want more practice problems, ChatGPT can honestly hook you up. That's where I get my practice problems from. But you can also look at the link down in the description for the limit comparison test. I specifically explain more complicated examples in those ones that you'll likely more see on exam. This is actually pretty likely to see on an exam as well. So if you get this, of course, it's just a review. But if you get this, then don't watch that. It is the next day. I just thought you guys would know that for no apparent reason. So we're going to talk about the telescoping series test now. And what is a telescoping series? Well, you can realize something is a telescoping series off of some pattern recognition by just simply looking at the series, or by expanding the series. So let's go ahead and start off with the number 2. N is equal to 2, okay? So since n is equal to 2, let's go ahead and expand this. We get minus 1 here, okay? So we get minus 1. The next sum is when n is equal to 3. So this is right now is n is equal to 2. Now we want to write the sum for n is equal to 3. So when n is equal to 3, we have 1 over 3 minus 1 over 2. All right, how about when n is equal to 4? Well, when n is equal to 4, we have the sum 1 over 4 minus 1 over 3. All right, and dot, 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 let's put plus dot, 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 and then plus with the general formula, 1 over n minus 1 over n minus 1, right? And this is just continues to go on and on and on for whatever n value we choose, this pattern right here. But what you can actually notice in a telescoping series is that this 1/2 cancels out with this 1/2. This 1/3 cancels out with this 1/3, right? Because the plus sign distributes into the 1/3, so therefore this 1/3 is positive. But this 1/3 is negative. So you add a positive 1/3 minus 1/3, and you get 0, right? So these cancel out. And actually, if you just keep going on, this positive 1/4 will cancel out because there's going to be some negative 1/4 in the next term of the sum. And if you keep going on and on and on, you realize that every term on the right cancels out first. So this is a key distinction between other telescoping series you might see. Most of them you might see, like this guy is going to be canceled out first, the term on the left. But as you can tell, if you just keep going on and on and on into infinity, right, as n approaches infinity, then you realize that the right term gets canceled out first. And this left term inside of your sum, or this guy, gets canceled out later on, right? But if n approaches infinity, what number is past infinity? Absolutely nothing. So if nothing is past infinity, that means there's nothing to cancel out this left term. Therefore, this guy gets canceled out. But this guy gets left behind. So if we were to actually make a formula for this, right, you're going to realize that you can actually create an equation that tells you the value at any n. And that is, if you keep going on to infinity, everything gets canceled out except for this 1 over n and this negative 1. So you get left off with 1 over n minus 1. Right? But technically, if we want to solve this series on to infinity, we need to set a limit to infinity for an n. Because this equation tells us, right? This equation basically tells us the value of our series at any n, right? The value of series at any n. So if we were to plug in n is equal to 4 here, right, we get 1 over 4 minus 1, correct? That makes sense. We have n is equal to 4 here, and we only have 1 over 4 and negative 1. So these two, this formula just basically tells us the total sum, or the value of the series at any n. So what about when n approaches infinity? Because that's what we're trying to solve for, right? Well, as n approaches infinity, we get 1 over infinity minus 1. 1 over infinity, simply just 0. So you have 0 minus 1, simply negative 1. So the value of this telescoping series is negative 1. And you're gonna see this pattern for nearly all telescoping series. Well, actually all telescoping series, not nearly all. You're gonna see this pattern for all telescoping series. You're gonna have something that keeps canceling out and keeps canceling out and keeps canceling out. Basically, the only thing you really have to do is just write down the sum up until maybe, like, if this starts off at n is equal to 1, for example, some series will start off at n equals to 1. The reason why this doesn't start off at n equals to 1, because if n was equal to 1, then you would have 1 minus 1 here. That's just 1 over 0. That doesn't make any sense. So that's why n started at 2 here. But if you start off with n is equal to 1, maybe write down n is equal to 2, n is equal to 3, n is equal to 4. Like the sum up to 4, maybe the sum up to 5, right? That might help you visualize it better. Cancel a couple things out, and you're eventually going to see a pattern. And with that pattern, you'll be able to find a formula for the series. And if you set that limit to infinity, then you're going to be able to solve the entire infinite series. Now we are on to the alternating series test. This one has just 3 very, very simple conditions that are quite straightforward. But let's go ahead and recognize what an alternating series is first. So what an alternating series is any series that has this term right here, right? Negative 1 to the power of n could be negative 1 to the power of n plus 1, n plus 2, right? It could just be anything that makes it so that your series will have the negative of the next number. So let's say, example, negative 1, 2, negative 3, 4, negative 5, right? This is an alternating series. This obviously doesn't converge, but this right here is an alternating series where negative 1, 2, negative 3, 4 basically switches from positive, negative. So usually when you're doing the alternating series test, you want to find the absolute value of this. And the reason why is you're just cutting out the alternating part. All right. So the alternating term in this case is negative 1 to the power of n. And you're going to have some general function a of n. Doesn't really matter what it is. It could be 1 over n. It could be 1 over n squared plus 2. Okay. It could just be that. But you just take the absolute value of this, which cuts out the alternating part, and you just get something called b of n. All right. And b of n, why am I writing this weird? B of n is equal to the absolute value of your series. Now, when you have the absolute value of your series, you simply, as I said, cut out the alternating part. So you just get a of n, basically, the a of n part. Now, as you have this, let's go ahead and look at the conditions. So, b of n must, I don't think I have enough space. I'll erase this, and I'll go up. The title kind of blocks away from most of these things. Okay, b of n. So b of n must be monotonically decreasing, or you can just write down decreasing. It doesn't really matter. What this basically means is that each term, next term, is smaller than the previous. Right. So in this case, negative 1, since b of n is the absolute value, b of n just has only turns every term to positive, so 1, 2, 3, 4. This is not monotonically decreasing. Each number is getting larger and larger and larger. An example of monotonically decreasing could be 1, 1/2, 1/3, 1/4, and 1/5. Right. Each next number is getting smaller and smaller and smaller. This is monotonically decreasing. Most of the time, teachers aren't very picky about saying the monotonically part, so you can just write down decreasing. You're also going to see this condition as well. B of n must be positive. But, I mean, like, if you take the absolute value of this, let's hope that b of n is positive. I really don't know in what case b of n would be negative if you take the absolute value of a of n. I don't know, maybe you do something weird with complex numbers, but like this, really, you don't have to worry about that. So this condition, it's kind of already guaranteed if you're taking the absolute value, right? And there's another one. Basically, this is the most important one. Well, I guess all of them are important, because if you don't meet any of the conditions, then you'll be done for. But this one specifies that the limit as n approaches infinity for b of n must equal 0. I guess I'll put it in red. Must equal 0 for convergence. All right. So you need to take the limit as b of n approaches infinity, and that must equal 0. So what if I were to give you an example problem? Well, an example problem would be 1 over, actually, negative 1 to the power of n over n. All right. So this right here is an alternating series, right? It has the negative 1 to the power of n. This is actually what we call the alternating harmonic series. Harmonic series, as you know, is 1 over n. So first things first, we take the absolute value of this to get b of n. If you were to take the absolute value of this, you cut out the alternating part, you just get 1 over n, right? So we have b of n is equal to 1 over n. This is our absolute valued series. Now let's take a look at the conditions for the alternating series. Is it decreasing? Well, if we take a look as n goes up for this series, n is equal to 1, n is equal to 2, n is equal to 3, you're going to realize that you just get 1 over 1, 1 over 2, 1 over 3. Okay, this is monotonically decreasing, right? Each next number is getting smaller and smaller. Is b of n positive? Yes, you took the absolute value, so it has to be positive, right? And does the limit as n approaches infinity for v of n equal 0? I'll tell you why this condition is weird later, but or compared to your traditional idea of convergence. But let's go ahead and determine that. Let's take the limit as n approaches infinity for b of n, right? And b of n is equal to 1 over n. Well, this equals 0, right? You get 1 over infinity, which is equal to 0. So this condition, and this condition all hold true. Therefore, your alternating harmonic series, or just this series, converges. Now, I'll tell you why this is weird. And this is weird because of the divergence test. Remember, in the divergence test, if the limit as n approaches infinity for your series is not equal to 0, then you determine divergence, correct? It was the first test I covered in this video. But if it does equal 0, actually I should have undone that. If it does equal 0, then your test is inconclusive technically. You cannot determine convergence off of this. Right? Well, alternating series states that if the absolute value of your alternating series equals 0, then you converge. So, you know, in contrast to the divergence test, where if your limit approaches 0, you get inconclusive, for the alternating series, you actually get convergence if the limit as n approaches infinity for your sequence equals 0. Right? In comparison, in contrast to the divergence test, these are polar opposites. Divergence test says this would be inconclusive, but alternating series test says that this is convergence, or this determines convergence. And this only applies to alternating series. All right, you cannot say that the limit as n approaches infinity for your sequence is equal to 0 determines convergence if it's not an alternating series. Right? This only applies for alternating series, so keep this in mind. You need this negative 1 to the power of n term. Now, if it was negative 1 to the power of 2n, this is not an alternating series, just saying. I'll just give you that hint real quick. And the reason why is because if you were to write down everything, you're going to realize that n, this power, is going to be only positive. It's only going to be positive, not positive, even. It's only going to be even. And if you put negative 1 to the power of some even number, you're always going to get some positive. You're always going to get positive 1, right? So let's move on to the next test. On to ratio test. So let's go ahead and talk about when or where and what cases you'll use the ratio test and how to recognize that you'll use it. Because of course, probably one of the hardest things about these convergence divergence tests is knowing which one to use. There's so many options. But for the ratio test, you will use You will use it when you get an exponent or a factorial. That is very likely. All right. You likely will use it when you get some exponent or factorial in your problem. Now, in this case, I put a practice problem on here because practice problems are probably one of the better ways to show you how to do something, right? There's a bunch of people that speak in really general terms. I guess that's good in some sense. Some people may learn like that, but from what I found, it seemed more helpful if I were to actually give you an example. So just think of this as a general series, A of n, where I'm using a ratio test on. But I'll work through this problem for you guys, show you how to use it. But let's first talk about the conditions for the ratio test. So for the ratio test, just like the limit comparison test, you have to take some limit. So we're actually taking the limit as n approaches infinity for a of n plus 1 over a of n. Now what does this mean? Simply, a of n plus 1 is your original series, but you replace everything, all the n values are just n plus 1. All right, and a of n is just your original series. So in doing so, in taking this limit, you'll get some r value. It could be capital R, it could be lowercase, doesn't matter. I think most textbooks use a lowercase. I think that's what my teacher used when I took calculus 2. So maybe you'll see it as that. But this limit is solely what determines convergence, divergence, or inconclusive. So if you take this limit, you're eventually going to get some constant, right? And that constant will tell you a couple things. If r is less than, greater than, or equal to 1 in all the cases. So if r is less than 1, then your series converges. If r is greater than 1, your series diverges. And if r is equal to 1, you get inconclusive. But this one is quite rare. Most people don't really get inconclusive for the ratio test. But be aware of this condition, of course. So you need to take the limit, right, as n approaches infinity for these two series over each other. Now, I have a video on ratio tests as well, and this individually explains the logic behind this test. So eventually, you really don't even need to memorize these conditions if you understand the logic. So I highly recommend that you watch that and understand it if you really just care about, just passing your Calculus 2 class. Be my guest. But of course, if you understand it, it's way better, right? But let's erase these conditions. I'll remind you of them later because I need the space. So let's take this test. Okay. So let's take this limit as n approaches infinity for a of n plus 1. A of n plus 1 is 3n plus 1 over n plus 1 factorial over 3 of n over n factorial. This right here is a of n plus 1, and this right here is a of n. Well, if you take this limit, you can evaluate this fraction to be 3 of n plus 1 times n factorial over n plus 1 factorial times 3 of n. Let's erase this. Once you have this limit, you can simplify this even further by expanding this exponent and expanding this factorial. How do you do that? Well, we can expand this exponent by using some exponent rules. So you have 3 to the power of n times 3 to the power of 1. Right? If you multiply two exponents with the same bases, all you do is just add their exponents, n and 1. And this is times n factorial over n plus 1 times n factorial. This right here expands. This right here expands into this. And you have 3 of n at the end. So what you actually notice is that a lot of the terms cancel out. This cancels out, this cancels out, and you just get left off with limit as n approaches infinity for 3 to the power of 1, which is just 3, over n plus 1. So this limit is actually quite simple to solve. And in most cases, the ratio test will lead to a pretty simple limit, but there's no guarantees for that. Hopefully your teacher doesn't do any of the crazy limits. But 3 over n plus 1 evaluates into 3 over infinity, which is just equal to 0. All right, so remember, when r is less than 1, then your series converges. All right, therefore, this guy converges since r is less than 1 in this case. Now, the reason why is because of this factorial. If the factorial is in the denominator, then you have an exponential in the denominator. Factorials always grow way faster than exponentials, right? 3 to the power of n is exponential. So, due to the fact that this factorial grows so much faster than this exponential as you go into infinity, all that's really happening is that you're just getting smaller and smaller and smaller. The numbers are getting so small, in fact, that you converge as you go into infinity. Now, keep in mind, if you had n to the power 4 over 3 to the power of n, exponentials grow faster than polynomials or power functions, okay? This is a power function. N to the power of something is a power function. And this exponential grows faster, right? So, in general, you can expect certain results using the ratio test if you just look at the factorial and exponential, right? So, that already gives you a hint of the answer. But let's move on to the last and final test. On to the last test. This is the root test. And usually, you're going to use the root test when you have any series to the power of n, right? If you can distribute the power of n, or you can factor out the entire power of n, it'd be very useful to use the root test. An example of this would be 2n plus 2 over 5n minus 1, maybe, all to the power of n, right? Or you could have seen it like this, where both the numerator and denominator to the power of n. But in fact, you can actually factor out this power of n, right, on both numerator and denominator, get the entire thing to the power of n. So why is this important? Why does everything have to be to the power of n? Well, the reason why is because the root test takes a limit. And this limit is determined by, again, the limit as n approaches infinity, for the nth root of a of n, right? This is the root test. So, if you have a of n to the power of some n, then you can actually cancel out this nth root and this power. So, that's why you want the entire thing to be the power of n with the root test, because it makes the limit very, very easy to solve. Now, let's go ahead and talk about the conditions of the limit, right? Because this limit determines everything. So the limit can be less than, greater than, or equal to all 1. If L is less than 1, or the result of your limit for the root test is less than 1, you converge. If L is greater than 1, then you diverge. And if L is equal to 1, then you are inconclusive. So, these are the possible situations. And now, let's give a problem. Let's erase this, And example problem would be, maybe 2n. Let's use the one I showed at the beginning. 2n over 5n minus 1, all to the power of n. So this right here is our series. We need to determine whether or not this converges or diverges. So erase the conditions for more space, of course. And remember, this limit is the nth root of your series, correct? Well, let's go ahead and take the nth root of this series. 2n plus 2 over 5n minus 1 to the power of n. What you can actually take out of this is, okay, I'm delaying a little bit. I'm trying to find time to write. What you can actually take out of this is that these cancel out, correct? When you have something, let's choose some variable x to the power of, let's say, x fifth root, right? This is technically equal to x to the power of 1 over 5. But you have x to the power of 5, right? This is technically x to the power of 5, right? So, if we take the fifth root of everything, then we technically have x to the power of 5 to the power of 1 over 5. And since we have exponents on exponents, we actually need to multiply these exponents together. If we multiply 1/5 by 5, we get 5 over 5, which is equal to x to the power of 1. which is equal to x. And if you had in the case n here, you technically have, let's use a different color. If you had the case n here, you would technically have x to the power of n, x is just any number, all right, and you have x to the power of 1 over n, times x to the power of n. And then the same thing, these n's would cancel out, n over n, which is equal to 1. So you would just get x left over, which is our series in this case. So since these n's cancel out by some rules of exponents, we actually just get the original series without the power of the n. So now that we have this, all we need to do is take a limit. Well, we realize that if you take a limit as n approaches infinity for this, then you're just going to get a horizontal asymptote. So when we take any limit as n approaches infinity, you only care about the largest exponents in the numerator and the denominator. What are the largest powers or exponents? Well, 2 to the power of n and 2 to the 2 to the power of n. 2 times n and 5 to the 5 times n are the largest exponents in the numerator and denominator. n approaches infinity for 2n over 5n. And technically the largest exponents because n is to the power of 1 here. The rest are just constants. Obviously, those don't have any powers or exponents, so kick them out. So now that we have this limit, what do? We realize that these n's actually cancel out, so we just get 2 over 5. And this 2 over 5 is actually equal to L. Now remember what we said about L. If L is less than 1, then you converge. Therefore, this series converges. Now, if I wanted to be more specific about the results of the ratio and root test, I would say absolute convergence. Technically, ratio and root test determines absolute convergence. I don't know why I didn't include that. I guess I just thought it was unnecessary, but it's just absolute convergence. Really, no difference between what if you were to just say it converges. I guess there's a little bit of a difference, but I covered the difference between absolute and conditional convergence in another video. And if I want to be a little more specific again, technically you're taking the absolute value of your limit. Same for the ratio and root test. But I know this has been a long video. If any of you guys want more problems related to these things, more worked examples, I've covered every single one of these tests with specific videos for them. So if you want a more specific explanation, want more practice problems, go ahead and look at those. But as always, if you have any questions, put it on in the comment section. And if you found this video helpful, consider subscribing and liking the video. Thank you for watching.